In this video, we continue the discussion started in the previous video. When the simple models we built in that video fail, it's time to think about using higher order polynomials. So the focus in this video will be to use higher order polynomials to fit as well as possible a dataset. In the previous video, we discussed about building relatively simple models with only one term that would fit a given dataset. We continue in this video that discussion. We focus on the situation when such simple models don't yield good enough results. The solution we discuss is that where the model will consist of a polynomial with more than one term. The main question we will address is how to choose this polynomial so we end up with the simplest possible solution for a good fit. Here is an example illustrating the problem we need to solve. Given 2 points, we can of course draw only one line through them. But there is an infinity of higher order polynomials that pass through those points. The situation is similar if we have 3 points. There is only one polynomial of degree 2 going through those points. But there are infinitely many polynomials of higher degree that pass through those same points. In fact, this observation is more general and has been known for a long time, for more than 200 years already. Here is what it says in its most general form. This is a result due to Waring in 1779 and later refound by Euler in 1783. It says that for any number of data points, say n plus 1 points for some number n larger than 0, there exists a polynomial that goes exactly through those points. Moreover, the polynomial is unique, it has degree n, and its form can be easily described as seen now on the screen. So this is a great result. Such a polynomial will always go exactly through the data points, no matter where they are, how many they are, and however randomly they may seem to be placed. The catch is this. There is a heavy price to pay for getting a model with a perfect fit. It's a polynomial with a very high degree. Given, say, 1001 data points, the model offered by this result will be a polynomial of degree 1000. A major problem with this is that such high-degree polynomials may jump abruptly between data points, thus predicting wild behaviors that are not justified by the dataset itself. Another problem with this solution is that it's extremely sensitive to the datasets. If we get just one more data point in addition to the other 1001 points we had, the model offered by this approach will be drastically different. So obviously, these are issues that cannot be accepted, and thus in practice, we must find other solutions. The aim will be to find an alternative solution that still offers a polynomial as a solution, because they have many desirable mathematical properties that makes them easy to work from a technical point of view. But on the other hand, we will aim to keep the degree of the polynomial as low as possible. When doing this, we will obviously have to accept paying a price. The model will not pass through all the data points as a high-degree polynomial would. Here is an example. So we have 10 data points, and if we were to get a perfect fit, we would have to choose a polynomial of degree 9 that may suggest a behavior something like this. But as a matter of fact, a concave curve described by a second-degree polynomial will in many cases be more acceptable, and it may look like this. This approach is called smoothing, settling for lower-degree polynomials, describing the data as well as possible, even if imperfectly, and avoiding the brusque changes that a high-degree polynomial often has. In this approach, the modeler has to make two decisions: what the degree to choose for the polynomial and how to choose its coefficients. The matter of the coefficients will be settled in the way we already discussed 2 videos back, using a measure of fit quality and finding the parameters that minimize the deviations from the dataset. We focus now on the question of which degree should one choose. In other words, what degree does the data suggest we should choose? A simple observation is that a second-degree polynomial p of x equals a plus bx plus cx squared has a constant second derivative and a zero third derivative. Indeed, the first derivative is b plus 2cx. The second derivative is 2c. And the third derivative is 0. We only have the data points, but from them we can approximate the values of the first derivative by simply taking the so-called divided differences. Here is what this means. Let's say that we have two data points, and they are at coordinates x1, y1, x2, y2. And through these data points, there is a curve that we need to discover that might look perhaps something like that. The way this curve grows between these 2 points is approximated by the slope of the line going through the 2 points. And the slope of this line can in fact be calculated as y2 minus y1 over x2 minus x1. And the slope is in fact the angle that it forms with respect to the horizontal. And that's exactly the idea. We might calculate these divided differences between each 2 consecutive points in our dataset, and they can be seen as an approximation of a sample on the first derivative of the model we look for. Then we can use these values to calculate the divided differences between them and get an approximation of a sample on the second derivative. And we can continue like that. The moment we get to 0 or to almost 0 values, we will get the answer to our question regarding the degree of the polynomial suggested by the data itself. Here is an example. Assume we have 8 data points shown in this table. According to our strategy, we start calculating the divided differences between these points. And let's take the first one, 205 and 430. So we can calculate the divided difference between these points as being 430 minus 205 divided by 200 minus 100. And that will give us 2.25. We do the same for the second pair of points, and for that we do 677 minus 430 divided by 300 minus 200, and that will give us 2.45. 47. We continue calculating these values and then we write them in the same table, somewhat vertically in between the original points, just to show the range of the x coordinates of the original points reflected in these differences. In other words, the first difference, 2.25, reflects the difference between some point at x coordinates 100 and 200. The same applies to the other differences as well. We can now calculate the divided differences between this new set of points. So the first divided difference will be 2.47 minus 2.25 divided by, and here you need to pay attention, it's going to be 300 minus 100, and the result is obviously 0.0011. For the x coordinates of these points, we choose the extremities of the x range that they represent. In our case, the first value was the divided differences between x at 100 and x at 200, and the second difference was from 200 to 300. So thus, we use for the current calculation 300 minus 100 in the denominator. We continue with the rest of the calculations, and the table is going to look like this. We then continue calculating the divided differences of the new set of data points, and the table will look like this. Obviously, some of these values may not be quite zero, but just very small. This would be the case for the divided differences between these points. And we wrote it as 0, it's almost 0 in fact, just a very small number. It's just a matter of choosing the precision of our calculations, and so these values may be seen as 0 for all practical purposes. Going into the details of how to choose the precision of the calculation in connection to the scale of the data is an important matter, but it goes beyond the goal of this course, and I will skip it. So, to conclude this series of videos on constructing empirical models, here are some rule of thumb guidelines. We should start by examining the data, and if there is a clear trend, we should try to build a simple single-term model. This may involve applying some data transformations and fitting the model. In any case, the final model should be verified against the original data. If this doesn't work out to get a good fit, then one can aim to build a multi-term polynomial model. The aim should be to get a low-order polynomial, in other words, as simple and robust model as possible.